Hello, everybody. This is an example of applying the criteria of the GCD between an element and the value of n to know if an element has an inverse or not in Z over NZ. So the example here is Z over 14Z, and we will check all the elements from 0 bar to 13 bar to know if they have an inverse and possibly calculate it if it's simple to do. So 0 bar never has an inverse because 0 bar never has an inverse. It only concerns elements which are different from the new element. Now 1 bar, and this is true for any value of n, 1 bar is always its own inverse because 1 bar times 1 bar is equal to 1 bar, whatever the value of n. Now for the other elements, we got to check if the GCD of the value we are looking for, n14 in this example, is equal to 1 or not. So the GCD of 2 and 14 is equal to 2. It's not equal to 1. So 2 bar has no inverse in Z over 14Z because the GCD of 2 and 14 is equal to 2. The GCD of 3 and 14 is equal to 1. Actually, 14 is 2 times 7. So actually, all numbers which have either a 2 or a 7 in their decomposition will not have a GCD equal to 1 with respect to 14. So here, actually, 3 bar has an inverse. So let's go again using this GCD criterion, as 4 is an even number. So the GCD of 4 and 14 is not equal to 1, it's equal to 2. So 4 has no inverse always in Z over 14Z. The GCD of 5 and 14 is 1. These are relatively prime numbers, so yes. 6 is an even number, so it has a 2 in its decomposition as well as 14, so the GCD of 6 and 14 is equal to 2. Same thing for 7. The GCD of 7 and 14 is equal to 7. So it's not 1. 7 bar has no inverse in Z over 14Z. 8 bar 8 is an even number. So the GCD with 14 is not 1. Actually, it's 2. 9 is 3 times 3. So the GCD of 9 and 14 is equal to 1. So 9 bar has an inverse in Z over 14Z. The GCD of 10 and 14 is 2. So it's not 1, so 10 bar does not have an inverse. 11 bar has an inverse because the GCD of 11 and 14 is equal to 1. 12 bar has no inverse as the GCD of 12 and 14 is equal to 2. And 13 bar has an inverse. Actually, what you can remember is that 0 is never invertible. 1 bar is always invertible. Its inverse is itself, is 1 bar. And third thing to know, n minus 1 bar in Z over NZ is always invertible. This is the example here, as n is equal to 14, actually 13 bar is invertible. And furthermore, its inverse is also itself is n minus 1 bar. So here the inverse of 13 bar is 13 bar. So that you can try to check why n minus 1 bar is always invertible and is always its own inverse. I give you 2 ideas. Try to make a little proof of it. Use Bézout's identity with n and n minus 1. I think you will very quickly find coefficients. Or calculate n minus 1 squared modulo m. I think it's a very quick and efficient way to prove that n minus 1 bar is always its own inverse. So now, what about the value of the inverses? So actually, there are 2 ways of doing that thing. The first one is to use the extended Euclid algorithm, or try to find an inverse, let's say because the values are small. For example, here for 3 bar, we know that 3 bar times 5 bar is 15 bar, and 15 modulo 14 is 1. So here it's quite forward to find that the inverse of 3 bar is 5 bar is z over 14z, and actually as inverses always go by pairs, the inverse of 5 bar is 3 bar. So here I'll let you do the calculations or try to find the value, but 9 bar and 11 bar are both inverses, one with respect to another. So here, from all the elements in Z over 14Z, we found that only 6 of them are invertible.